everybody. Welcome to another Bay Area Rust Meetup. I'm very happy to have you all here, and hello to the internet. Tonight we're going to be talking about all the really interesting things happening in the input-output system, both in Rust itself and also in the greater community. Before I begin, though, I've had a request from some of our hearing-impaired community to help live caption the meetup. So if you want to help out, or if you just want to read the captions, follow this link. So, and once again, thank you, Mozilla, for feeding us and hosting us and live streaming us. It's great. Tonight we have, I forgot to say what Alex and Aaron were talking about. They will be talking about the Rust alpha that's supposed to be happening soon, and the standard I/O stuff that they've been working on. Carl from the internet will be talking about his Mio project, and Jonathan will be talking about some primitives he's building on top of it. Now, in the broader community, we have a lot of events going on. I just announced on the March event, which is all going to be about data science. I convinced my company's chief data scientist, Josh Wills, to talk, which is very exciting. And we're also going to have some other data scientists talking about algorithms and implementing them in Rust. It's going to be awesome. And finally, if anyone has any interest in talking about anything, please come and talk to me. I'm always looking for presenters. Anyway, enough of me. Now it's on for Aaron. Thank you. Please give him a warm welcome.
Hey, can everybody hear me? Cool. Just wanted to say thanks, Eric, for running these. These events are awesome. Really appreciate it. My name's Aaron Teran. For those of you who don't know me, I'm a member of the core team working on Rust here at Mozilla. Alex and I together have been working on what we call I/O reform, which is mostly what I'm going to tell you about today. But before I get into the details of I/O reform, I also want to give a sort of overall status report of Rust 1.0, which is drawing closer by the day. I'll cover sort of the overall principles for the I/O reform we've done, and then I'll dive into two particular API designs, and then Alex will follow up covering some others. So let's talk about 1.0. I'm sure some of you are following this stuff quite closely, some of you less so. So I wanted to just sort of lay things out graphically. We made some big announcements recently. The most important is there is actually a firm date for the 1.0 release, which is May 15th. It's about 12 weeks from now. So I'm told that the Alpha 2 build is completing as we speak. It should be ready to ship tonight. So it'll either go out tonight or tomorrow. And after that release, and I'll tell you a little bit more about Alpha 2 in a second, we have sort of a couple more milestones before we hit 1.0. So March 9th, in a few more weeks, is what I'm marking stable, and I'll explain what I mean by that. And then we'll put out a beta 6 weeks from now before we hit 1.0. OK, so let me go into a little bit more detail about what each of these milestones represents. So Alpha 2, the thing that we just hit, basically represents feature completeness across both the language and the standard library. And there are a few quibbles here. There are a few minor features that didn't quite make the cutoff, but we're essentially where we need to be for 1.0. So from here, for the next 12 weeks, we're basically going to be working on polish and tweaks. So first of all, just a call to arms. This is a great time to really start testing these APIs, giving us a lot of feedback. This is sort of our last chance to make tweaks before we really lock things down for 1.0. OK, another thing, we've been sort of gradually building up this stability system, right? So a big part of Rust 1.0 is that we finally stop breaking the world every day. In fact, we stopped breaking it altogether. But it's been a gradual process. So we've been making a sweep through the entire standard library basically cleaning up and making more consistent APIs, and then marking them as stable, which will become a promise that they would never change. We decided to do a second alpha release in part because of the stuff I'm going to tell you about tonight with IO reform. Although that stuff is all landed, some of it landed pretty recently, so we want a little more time to reach the stability marker. So this March 9th date marks the point where basically all the major libraries have been mostly marked stable. It should be possible to use only stable features to build up sort of real libraries, real applications. After that, by the time we hit beta, we hope to have worked with all of you and the broader community to move the ecosystem over from sort of nightly releases onto the stable channel. And then finally 1.0, we're sort of generally open for business with the broader world. Okay, so what does this mean for you? Like I said, right now, this is a great time to start kicking the tires a little bit more heavily, giving us last bits of feedback so we can make some tweaks before we nail this down. After we hit the stable marker on March 9th, that's the time to really push to try to get your crates running on the stable channel and letting us know where we have some gaps so that by beta, you're up and running. And then after beta, help us test and polish so that we can sort of put the best spin on things when we actually release 1.0 to the whole world. Okay, so that's the 1.0 status report. Any questions about any of that stuff before we move on? Cool, okay. All right, so let's talk about this IO reform, which is like the major thing that happened in the library since Alpha 1. Okay, first of all, like, why did IO need reforming in the first place? So I already mentioned that part of the preparation for 1.0 has been sort of scrutinizing each and every API in the standard library. So this was part of that process. But what we found when we looked at IO is a combination of things. First of all, there were numerous specific problems. I'll talk about a few of those tonight, like just various things that had cropped up over time with APIs. The details aren't too important, but you can read about them in the RFCs. I think a general problem was that Rust IO story has shifted a lot over the years. Originally, we had green threading, we were binding to libuv, and a lot of the design of the library sort of centered on those decisions. So this was partly reevaluating the APIs, with an eye to where we want to go next. And if I wanted to give a TLDR, I would say the IO library was previously lacking sort of solid design principles that were followed throughout. So we tried to set those out and then go make all the APIs consistent with them. Just for history's sake, this was sort of the timeline of what happened. We got started with this at the beginning of December. We had a lot of fun going through the RFC process. Thank you, everybody who gave us feedback. It was invaluable. The community really helped us a lot to get this over the line. Okay, so what are we actually trying to do with IO? So these are sort of the goals that we came up with post moving away from green threading. So this is like Rust 1.0 IO story. First of all, we are only tackling blocking IO. That is not to say that we believe blocking IO is the only thing that's important. You'll be hearing lots about async IO tonight. But it's a good foundation. It does have its uses. And it's something we understand reasonably well how to do in Rust. So our goal was to make our blocking IO story as good as we can without sort of precluding us from doing good async APIs later on down the line. In terms of coverage, we wanted to make sure we had basic support for reading and writing files, sockets, spawning processes, and so on, enough to code like an Apache-style server, that kind of thing, which were definitely there. Another change was a move towards zero-cost abstraction. So basically, not trying to provide a lot of functionality in the standard library IO over what the OS provides. So mapping a little more closely to the OS surface. And we'll see more what that actually means in practice later. Of course, the most important role of the standard library in some sense is like defining traits that everybody can use as a common language. And that's especially true in IO with what used to be called the reader and writer traits, which are now read and write. And it turned out actually there were several subtle problems with the old traits. And Alex will talk more about that. Okay, and then finally, a big theme was sorting out the story of cross-platform versus platform-specific APIs. What kinds of cross-platform guarantees do we want to provide? How do we provide hooks for doing more low-level stuff if you want to get underneath std? Okay, so this is a lot of stuff, and obviously we're not going to be able to cover all of this in any detail tonight. You can read more in the RFC. But again, if I wanted to summarize those goals, I would say the direction has been be conservative. So more and more we've become less opinionated in the standard library. We've tried to be less abstract. We've tried to more faithfully represent the underlying system and sort of let people out in the broader ecosystem develop those cooler abstractions that we used to try to provide more directly. And I think that's been working out pretty well. Okay, so now I'm just going to focus on a couple of those topics in more detail, and then I'll hone in on some specific APIs. So one of the things that was most contentious and we had to think really hard about was our cross-platform story. First of all, just to vent, cross-platform API design is really hard. Like any API, there's always some difference you have to account for, and trying to make the surface pretty, hiding all of that stuff is really hard work. So one of the things that changed with this reform is we now provide, in the sort of standard library surface, only services that are like reasonably close to being cross-platform. So just to pick an example, Windows comes with pretty good support for timeout waiting on a process that you spawn. Whereas with Unix, we actually spawned our own helper thread and set up like a timer to try to coordinate that to provide similar functionality. And that stuff is gone. So we're only like mapping services that the OS actually provides directly on all the platforms we support. And of course, we want everything to match Rust conventions and API design principles. That means we're not using POSIX names everywhere, for example. We're trying to make this just a Rust-centric library. On the other hand, platform-specific stuff is really important too, right? Maybe you're coding something that is Unix-specific, and you want to take advantage of ePOL or KQ or whatever. And so we've also sorted this story out as well by introducing some new API surfaces. So we have a module called OS, and under OS, there are a bunch of different platform names. And they're not mutually exclusive. So there's the Unix platform, and that includes Linux, macOS, and others. And then you can get more specific and ask for Linux-only features. And the cool thing about this is it's very easy to grep your source code for places where you're doing something platform-specific. If you're not using an API in one of these modules, you're using cross-platform stood APIs. And the other thing is we set things up so that the stuff that you do get in these platform-specific modules hook into the rest of stood via things like extension traits. So basically, if there's extra functionality one OS provides, you can import that and then use the rest of the standard library as if that was sort of a native thing that it provided. So it all feels very seamless in the end. A couple words about the overall organization. We previously had like a big I/O module with everything underneath. Now that's flattened out, so we have a bunch of modules understood. Let me just point out a couple interesting ones. We have an FFI module that's useful if you're doing anything that's talking to C APIs. And I'll talk a little bit more about that later. The I/O module now contains just the sort of abstractions that I/O provides in adapters, so things like the read and write trait and various ways of hooking those together, memory buffers, that kind of thing. We have a I/O-specific prelude. So none of I/O is included in, the standard prelude anymore. But if you're doing I/O heavy work, you can just glob import everything from prelude and you're good to go, from I/O prelude and you're good to go. And then finally, there's the platform-specific modules that I already mentioned. So those are kind of the interesting bits. OK, any questions before we move on to the next section? OK. All right, so now I just wanted to cover a couple of interesting API design points in a little more detail. So the first one is what we call OsStr, and this one was really thorny. So it turns out that this is roughly the situation for more or less idiomatic strings on the different platforms we want to talk to. Okay, so on the right, we have the Unix world, which operates in C strings, which are basically null-terminated sequences of bytes. Okay? So they can't have any interior nulls. On the left, we have Windows, which uses something sometimes called UCS2, which is a lot like UTF-16, but not quite. And in particular, basically any sequence of U16 values that doesn't have a null is valid UCS2. OK, then there's an intersection, which is if you have UTF-8 encoded data without any interior zeros, that is something you can make sense of in both platforms. And then, of course, in Rust, we also have UTF-8 data with interior nulls. So we have this whole mess of things to somehow put together. Now, oh, right, sorry, I just mentioned this. So with Rust, it's UTF-8, and that includes interior zeros, which you can't make sense of as a C string. So in old I/O, this was the story, basically. It was either, if you were talking to Windows, we just pretended that Windows talked Unicode only. And if you were talking to Unix, then you got C strings. But that's not right. Okay. So what we managed to do with the I/O reform is actually introduce a new type that captures this entire space of types in more, well, it's something approximating a single encoding. So in particular, if you are running on Windows, then OsStr captures this segment. So basically UCS2 plus a little bit of extra stuff that you get with Rust. And if you're running on Unix, you get the other side. Okay. And making this work is kind of interesting. Unfortunately, I don't have time to go into the details, but I'll mention an important encoding in a sec. So this OsStr type, we're taking sort of full advantage of the new features that have landed in Rust, like DST. So we have, just like we normally have our capital string type and our lowercase str slice, we have an OsStr owned type and an OsStr slice type. And one of the cool things is if you want to go from a Rust string to an OsStr, that is an absolutely free, that's a no-op, basically. Being able to do that relies on an encoding with a wonderful name called WTF8. Simone Sapan is somebody who works at Mozilla on Servo, and he actually wrote an honest-to-goodness RFC about this encoding format. It's a really good read. So we're using that internally for OsStr now, and that's what allows us to sort of hit all of the bubbles that I mentioned before. And then if you're on Unix and you have an OsStr, you can get out a sequence of U8 from it, and on Windows you can get out a sequence of U16. So it all sort of works out in the end, but we did have to introduce a new string type to make this all work smoothly. Any questions about OsStr? This is probably, in terms of being conservative, this is in some sense in one sense it's the least conservative because this is a pretty radical change. But on the other hand, it's actually being a little bit more honest about what each platform string type is. So, okay. The other thing I wanted to talk a little bit about was paths, which were also reformed as part of this project. So we had a pretty decent path module coming in, but like the rest of I/O, there were some problems that accumulated over time. So first of all, it made the same encoding assumptions I mentioned before, that sort of on Windows everything was Unicode, which is not actually true. It had some ergonomic problems. So anybody who's used it is probably aware of this. Like every method came with 3 different variants. Do I want this thing as a path? Do I want it as a string? Do I want it as a sequence of U8s? And it also was pretty aggressive in normalization. So it would normalize away parent directory links, which is sort of well known to cause problems with symlinks, because basically this normalization breaks the semantics of paths. So these were some of the problems we wanted to address. And basically, we followed the same pattern that I just laid out with OsStr. So we have an own type and a slice type. It's actually just a wrapper around OsStr, so that takes care of the encoding issues. But the nice thing is, by using this new slice type, we can solve the ergonomic problem as well. So basically, all of the interesting methods for extracting directories, files, etc., just give you a slice back into the path. There's no allocation. There's only one type. And then there's just a single method given a path you can ask for a string, which will tell you if the string contained non-Unicode data, and then you can deal with that separately. In terms of normalization, we're really conservative. So we only normalize repeated separators, basically. But we haven't done this yet, but it should be very easy to add a sort of whole Swiss Army knife of normalization options on top of that. So this I really want to draw attention to in terms of places we could use feedback. Please try out the Path API and tell me whether you run into problems with normalization or not. So I hope to land the normalization adapters soon, but it's not clear whether this very minimal option is the right default. So I could really use some real-world experience to help drive that default choice. And then just a quick word about the implementation, because I'm pretty proud of it. It's tiny, and basically it's a showcase of the way we do things in Rust. The entire thing is built on a single iterator. So if you're bored one night, it's a tiny bit of code to read, and you can sort of see all the new stuff we've been landing in Rust working together to make a nice API. OK, so that's it for the detailed part. I just want to go back and sort of mention the big picture again. So I laid out a bunch of goals for I/O reform, and I'm happy to say I think we've achieved all of them. I think that if you look at the new API, it satisfies sort of all of these constraints. That said, I mean, the coverage is fairly minimal right now. There is some stuff that would be really nice to do for 1.0 if possible. Probably the biggest one is we ended up removing socket timeouts for various reasons. I think we can probably get that in the 1.0 timeframe. There are some other things, some platform-specific extensions. I was just talking to some people about this earlier. This is also an area where your feedback would be really helpful. Like, take a look at the new I/O surface. What's missing for you? What do you need for your app? And then just a meta point. So I wanted to thank Alex in particular and Kevin Ballard, who designed the previous Path API and helped me design the new one over some sandwiches at Ike's. And also thanks to the whole community for a really great round of RFCs. I think this was a really successful project. So that wraps it up for me. Thanks. Be glad to take any questions before I turn it over to Alex.
So when you're using Windows APIs, so when you're using
I'm not sure that's on.
So when you're using the Windows APIs, there's no way to avoid converting to the 8-bit bytes or 8-bit characters and then back.
Right. So OK, this was definitely a question that was debated in the RFC process. So basically, Rust long ago made a decision to make its native string type use UTF-8 always. So basically, if you're writing idiomatic Rust code, you're going to have to pay an allocation and conversion cost when you hit a Windows System API regardless. The main question is when in the pipeline does that happen? And the way we designed OsStr, basically you stay in UTF-8 for as long as possible. If you're calling down to a System API, you convert at the last minute just before you call the System API. And part of the rationale there are basically two reasons we ended up doing that. One is if you're calling a System API, it's generally something expensive anyway, so the cost turns out to be negligible. But also, if you think about things like paths, this means you can do a lot of path manipulation internally, stay in UTF-8, get UTF-8 back out without ever paying that conversion cost. So if you're doing path manipulation but not actually calling a System API, you've saved in that case. But there are other cases where you lose. It's sort of an unavoidable cost. Any other questions? Cool. All right, thanks again. Let's see. I hit play. Oh, wait a minute. Should I see it here, but not here. Is that okay?
The resolution is too high for the stream. You have to lower your resolution.
All right. Perfect. All right. Hello, everyone. My name is Alex Creighton. I, like Aaron, I work here at Mozilla as well. I'm on the core team, and I'm going to give you, Aaron, kind of give you a little bit of a high-level tour of what the concepts of I/O was, a little bit of OsStr and Path, which kind of fed into all of this. I'm going to give you more of a whirlwind tour of kind of the specific APIs that we have, both in std.io, FS, and net. These are some of the ones that I kind of pioneered. We're leaving out process, I think, primarily for now, but we can always talk about that later. So the first thing I want to talk about is std.io, and like Aaron was saying, this is a lot of the
impetus behind Style.io was to kind of lower the level of abstraction of the primary, the reader, and the writer traits. You'll see that in a second. And that involves avoiding throwing away information. So you'll see that some of the previous APIs that we had actually kind of discarded some information along the way, which was unfortunate if you're using it in these more robust use cases where you're using it as kind of a basic building block for tons and tons of libraries. And not only that, but I'll point out tons of places where we have slight little modern Rust would have designed it a little bit differently than it was when it was actually designed, which was way, way long ago at this point. And then this general assumption that we may not be able to assume that everything blocks forever. We should at least consider these traits with an async IO perspective, although we're not designing them for async IO. So in that sense, I first want to talk to you about the read trait. So this is the trait that actually used to be called a reader. And on the surface, you might notice the only change is actually just the name. It goes from reader to read. And the reason for this is a lot of times nowadays, if you have one trait with kind of defined by one method, you just name it after the method. So this is kind of following that tradition where it's just following Rust APIs. And so this primary read method is actually pretty simple, and it actually didn't change from the previous incarnation where you just give it a buffer, you read into it, and then you return how many bytes are read. What really changed from this one were a lot of the extension methods, a lot of the adapters, and all that fun stuff. So if you look at the previous reader trait, there's this gargantuan litany of all these read and write methods for each primitive type, and there's all this fun stuff going on, and it's kind of hard to follow sometimes. So we decided to kind of take that encoding aspect and just jettison all of it, leave it all for later. We might be able to add it back later, but the core trait primarily has two useful methods for reading to the end and reading into a string, which I'll talk about these in a second, the differences, and then also a whole bunch of new adapters, which actually were not present on the original reader trait. So this read to end and read to string method, the major difference is that these take a mutable buffer instead of actually returning a buffer. So the old ones actually return to vec of U8 or return to string, but this has two primary drawbacks from it. So in the read to end case, if I have a stream which reads about 10 bytes, then it hits an error, the previous API would have actually just discarded those 10 bytes, and no one would ever know what those 10 bytes were. But if we are given a mutable buffer, we can actually put the bytes in there, and we can still return an error saying what happened, but at the same time, you can still retain information about what bytes are read. So in that sense, these APIs are no longer lossy. They actually retain as much information as possible, a lot of progressive information, because we're having call the underlying read API in a loop. So the read to string is somewhat like that. You don't get quite the same benefits because the data you might have read up to that point may not have been Unicode, and strings are always UTF-8. So you don't quite get that benefit, but the other major benefit you get is pre-allocation. Given these buffers, you can actually pre-allocate a space for all your data to go into, whereas previously you just kind of had to assume that we chose a somewhat nice number that wasn't too big, wasn't too small, all that fun stuff. So that's kind of the motivation for moving these return values into mutable buffers, which makes them a little bit less ergonomic to use, but it makes them much more robust in terms of usage. So these adapter methods at the bottom as well were basically us taking a leaf out of Iterator's book. So what we did is we had all these types, but they were sitting off in their own IO-util module, and you had to go call the constructors like, I think it was chain reader : new, or multi-reader : new, or limit reader : new, and it got kind of wordy after a while. But using kind of the iterator methods of just having an adapter that consumes the entire object and then makes a new one actually made these really ergonomic and really nice and easy to use. So we have this whole mess of things where you can really easily just limit a whole stream of bytes. You can convert a reader into iterator of bytes and iterator of characters. All this fun stuff going on. So and then the readx, like this split between read and readx, might actually go away in the future due to some recent RFCs. But you don't actually have to lose any ergonomics in terms of importing all of these fun traits all over the place, because these are all located in the IO prelude that Aaron talked about. So all you got to do is import the IO prelude star, and you have all these fun methods in all your readers and writers. So that's the read trait. And the next thing, the other pinnacle of IO is the write trait. So this is the current definition of the write trait, basically, and you'll notice this is actually fairly fundamentally different from the old writer trait. And the major difference here is this write method no longer returns unit. The previous writer trait guaranteed that given a buffer, it would only return success if it wrote the entire buffer successfully. Now, this isn't really, it kind of adds a layer of abstraction. It adds a layer of, well, now if I call a syscall, I got to go call a loop and kind of keep writing until I write the whole thing. And I got to assume that's probably blocking underneath, so I'm not just hogging the whole CPU while I'm sitting there writing in a loop. So in the spirit of kind of lowering the abstraction level and maybe making it a little less ergonomic to call, but becoming applicable to far more use cases, this now returns the number of bytes written. So this all of a sudden becomes appropriate for other protocols like non-blocking applications, because you may not actually be able to write the entire buffer all at once. So you actually know how much you wrote, and then you can go do something else with the intermediate data based on whatever application logic you have there. And other protocols like UDP, where it actually really matters about how much you wrote, and because something might have been truncated along the way, this is much more useful for them as well. So the other, another major difference is the flush method is no longer default. We no longer by default say that you return OK from flush. We now require that every implementation of write has to at least consider the concept that it has some sort of intermediate buffering, or it's wrapping something that it needs to go call flush on. So it's not really, it's something that has to be considered and kind of ensures that we propagate flushes all the way throughout the stack. And then like reader, we have a couple of extension methods on here. There's not quite as many because there's not as many adapters that we could think of. The write format method is kind of just this general thing to work with the write macro. And the byref and broadcast is to the multi-writer case. But the interesting one is write all. So write all is actually just the semantics of the old write method, where it says, I will, given a buffer, attempt to write the entire thing. So this is where, this is one point at which we have said that this is a lossy API right now. If you write a huge buffer, but it cannot actually write past the middle of it, because it hits some sort of error or it hits some sort of intermittent thing like that, you don't actually know how many bytes are written. But this is a point where we say that it is way more useful to actually have this method than to completely remove it altogether, because it's probably just going to end up being re-implemented in most code bases regardless. So the idea with this method is it only returns success if the whole buffer was written, and if it wasn't written, you don't actually know how much was written, and you just kind of have to, you can only call this API if you're actually comfortable with that in the first place. So some other utilities which we've now had designed around as first-class citizens of the new I/O module are a lot of implementations on primitives themselves. These were kind of added very late after the fact for the old I/O modules, but this is kind of a very prominent use case. So in this case, in-memory buffer can implement read, because whenever you read some bytes, you just kind of increment the pointer in the slice and you just keep moving along. It's most certainly a buffer reader, and then you can write into a mutable buffer, or you can write into a vector where it just pushes more elements on. And these are actually they can be very, very efficient implementations, and they can be very good for benchmarking or just general performance-heavy code, which actually needs these highly optimized implementations. And then along that, we have some other nice little adapters, kind of like the iterator module, which has the repeat adapter and some count adapters. But for I/O, we have a sync, where you can write a tons of data, and it just drops it on the floor and doesn't worry about it. It's like dev null. Empty is something which, when you read from it, doesn't actually read anything. And then repeat is something that is like the repeat in the iterator module, just yields the same byte a very large number of times. So these kind of make interoperation and kind of some small protocols a lot nicer to use, because you can really easily chain all these together and get all the nice robustness out of it. And one of the other primary additions to the stud.io module, which is new, is the cursor type. So this was previously incarnated as memreader, memwriter, buffreader, and buffwriter. And we were able to move all those types, which are kind of confusingly named, because you never know which is for a vector and which is for a slice, and why it's mem and why it's buff. And with cursor, we basically took these ideas and we say, all right, from this, we actually have a lot of capabilities, but we're missing primarily, like, I can't read from a vector, or I can't, well, that's actually the biggest one. So with cursor, it's just encapsulates the concept that we have one pointer into something. It's just a U64 that says, here's the pointer into my file, and then I'm wrapping something else. And then we have specific implementations of seeking, reading, writing for each of these primitives. So now all of a sudden, with one type, we're able to get all this fun stuff for seeking around in all these memory buffers, for reading vectors, for having an own reader, and all this fun stuff wrapped up into one little small package. So that's kind of the stud.io module, kind of walking through that and some of the major changes that we saw there. And I'm going to talk a little bit about stdfs. So stdfs is the replacement for std.io.fs. And as Aaron was saying, some of the high-level changes we're making are moving away from all the Unixy names. So unlink is no longer the way to remove a file, or mkdir is no longer the way to make a directory. Those are very Unix-biased and don't really make a whole lot of sense on Windows if you look at those. And it's kind of unfortunate if you're from Windows looking at stuff like that. And then I'll give you some examples of how we're focusing on cross-platform compatibility and how we're allowing you to still use all these fun APIs on each platform, but we're maintaining a cross-platform surface at the stdfs layer. And then as we're taking a look through the module, we can add some things like iterators, adding nice functionality there. So the primary change that you'll see is every method which used to take an ampersand path now takes an as path. And what this means is you can call it with a whole number of types. I can call it with strings, I can call it with OS strings, I can call it with paths, I can call it with path buzz. It's actually really nice to use. Most of the time, if you have a literal string, it's a lot nicer because you don't have to have ampersand, path, colon, new, and all that fun stuff. So this kind of makes the APIs much more ergonomic to use at the usage layer, and at the implementation layer, we can convert everything to paths at zero cost basically and push it on back down. The other major difference is how you create files. So we still have the standard open and create, which opens a file and creates and or truncates a file. But we previously had this open mode method, which took a file access and a file mode, I think. I never really quite remember. Which if you wanted to use, you had to import 3 different things and call this very long method, have a bunch of enum namespaces, and it's just very unwieldy to use. So for this, we took a leaf out of the commands book of the std process now, where we're using a builder style pattern to configure how you actually open a file. So in this case, you can just create this generic options, and you can chain a bunch of methods to say, I want to read it, want to write it, want to truncate it, maybe you want to open it exclusively to make sure it's not actually already there, all this fun stuff. And then at the very end, you can actually say open and open the file that you actually intend to. And one cool thing you'll see about this is that this is where we're designing around the cross-platform extensibility as well. It's very easy to, on Windows, add some fancy stuff about like some creation dispositions or some security attributes or all this fun stuff on the open option structure. So you can just have all these new methods only on the Windows platform. Same thing for the Unix platform as well. I'll show you an example of that in a second. So another API which I find pretty cool is how the readdir function changed. So at the surface, it didn't change a whole lot. This used to return a vec of paths, but now it primarily returns a iterator over dir entries. Now, the vec to iterator transition is mostly just becoming a little more ergonomic, and that's actually matching what the system API is. The system API is an iterator, so it's much better to expose that as opposed to making sure everything is all in a row and a line and a vector. But the choice of using a dir entry was actually somewhat motivated by, I think Hewan found an issue in Python from about like 2 years ago or some point, that when you stat a bunch of files in the file system or get the readdir information from them, you get meta information sometimes. Like on Windows, you have all this information about the size of the file, what kind of file it is, some extra extended attributes. And on Unix, sometimes you have the mode, sometimes you don't. It kind of depends what platform you're on. So we can use this dir entry structure, which you can, of course, still get a path from, which is what you primarily want. But we can add all this extra information later on. We don't quite have it implemented just yet, but it's adding room for future extensibility where you can query, is this a file, is this a directory? And that can actually, if you're walking a whole directory tree, sometimes you can improve your walk times by, I think the statistics said like 50 to 100% on some platforms. So one of the things in stdfs was the overhaul permissions. So this used to be just a whole bit flags thing. It was just known that it was an i32 pile of bits, and it was exactly what Unix did. And then if you think about that on Windows, you think, wait, this doesn't actually work. It doesn't have any analog on Windows. It's way more complicated on Windows and a whole different system, and it just doesn't map well. So what we did here is we pared this back. We removed all these constants. We removed all this like known structure of it because it's different. And we gave it to just a structure permissions. And then we have only one public method, which is cross-platform, which is read-only, which is kind of unfortunate if you want to do lots of fancy stuff. But unfortunately, this is all we can really expose cross-platform on Windows right now. But this is one case where we can get the OS platform extension traits. So in this case, we can see that there's an OS Unix permissions X trait, where it adds methods like the mode on Unix. So on Unix, you can actually get the piles of bits out, and you can check is it readable for the user, is it writable for others, or all that fun stuff. But this is not available on Windows, and this is where you can see that on Unix, we can give you all the fun access to everything, just not at the cross-platform layer. And then we plan to add all this fun stuff in the future for Windows as well, but I'll talk about that in a second. Or maybe later as well. So now I'd like to talk a little about stdnet. That was kind of stdfs kind of blowing through some of the higher level changes. There's lots of other little minor things about renaming, like makedir was creator now and fun stuff like that. But that was kind of the high level. So at stdnet, keeping in the tradition of the std.io reform, we're really scaling back the abstractions here. Previously, I mean, one of the worst offenders was this. When you created a TCP listener, you actually opened 3 file descriptors. Probably didn't know that when you were creating it originally, but it's kind of unfortunate that we were forced to do that for various implementation details. And so another thing we did with this design is we planned for concurrency from the start. So this was kind of bolted on after the fact when we realized people want to read and write concurrently on the same TCP stream, which is kind of useful sometimes. And we want to make sure that it was designed in from the start, ready to go from day one. And then a lot of this moving closer to system APIs, making sure we can expand this to more functionality in the future, it's all set and ready to go. So the first things to be kind of overhauled are the IP and the socket address types. So this was largely thanks to Kate Tossell on GitHub. He did an awesome job with redesigning these types. And at a high level, we have a socket address, which is no longer totally public. You actually have to have function accessors, so we can keep the representation private, which actually is the raw representation. It makes it kind of fun. And then the IP address types, actually the v4 and the v5 got their own separate types, so you can query fun things like, is it a loopback address, or is it like a, what's the multicast scope on IPv6? I don't totally understand all of it, but you have lots of fun accessors and abilities to gain information out of that. And then we also started to standardize this 2-socket address trait. Just the notion that from a thing, you can get a bunch of socket addresses. And this is primarily meant for DNS resolution, where I can, from a string, a host name, I can actually get a bunch of socket addresses. Or you can also say from a socket address, I can get a bunch of socket addresses. So this allows you to make very nice APIs where you can say TCP stream : connect to google.com or to 127.0.0.1 : blah, blah, blah. Speaking of TCP stream and connecting, this is the highlights of the new TCP stream API. This is not everything. We have a whole lot of other methods as well. But you can kind of see from the connect method, we make sure to take the 2-socket address trait to make everywhere we're taking addresses now, ensure to take 2-socket addresses so you can pass in host names or socket addresses or pairs of these two or fun like that. But one difference is we used to have this close read and close write methods. And those have been removed in favor of just calling shutdown now. We're exposing that shutdown is being called at the system layer. We're just putting that at the API layer. It's totally cross-platform, and it just tells you exactly what you're buying into. And it's kind of the same way with try-clone as well. TCP stream used to implement the clone trait, but the primary guarantee of the clone trait is that it's infallible. Once you actually clone, you're guaranteed to get the new thing out. So this was actually implemented with an ARC under the hood, but that's kind of unfortunate to impose that level of abstraction. So in this case, we're just calling dupe or WSA socket, duplicate socket, or whatever it is in Windows. And then you can kind of see the concurrent aspects of this as well, where we do have read for TCP stream, but the problem is that read requires a mutable self. And by requiring a reference to TCP stream, you can actually borrow the TCP stream and then read into it. Because the problem with mute self is if you have mute self, you're guaranteed one unique reference to it, but that doesn't allow for concurrency. This is where the read and write traits don't necessarily give you concurrency from the beginning, but we're still giving it to you at the TCP stream layer itself. So the TCP listener type didn't change a whole lot. The major idea was accept no longer takes mutable self, so you can accept many connections concurrently. And then it also gives you both the socket address and the TCP stream, which all the platforms give us, which we were just hiding previously. Same thing with try clone. The idea is it's no longer implementing clone, but you can still opt into it if you want. It just might fail. UdpSocket saw similar treatment. There's not a whole lot new in this respect. It actually stayed as a pretty consistent API as to what it is today. Just a few things moved around, and that was pretty much about it. So the biggest thing was that Aaron also alluded to is on TCP streams and UdpSockets and also TCP listeners, timeouts are gone. This is a pretty big feature of the API. That was what required a lot of this kind of extra file descriptors per listener and things like that. But we plan to add these back later with the various socket options on the stream types. And then the other types like listeners or connecting and those kinds of timeouts we plan to add on later or give you the ability to add it later, but we might not necessarily do it ourselves because it actually ends up imposing all these other extra abstractions. And then the other primary reason is we're still waiting on std time to actually stabilize to get a duration type so we can actually write this method signature in a stable way. And there for example, Aaron talked about how process requires a helper thread, which is why we're probably not going to add it back. Things like TCP listener require some extra file descriptors and connect. We'll talk about that in a second. So I want to talk about now about how we might extend these APIs in the future. During all these RFC discussions, we got tons and tons of questions, tons of requests, all this fun stuff, and we really do want to implement all of it. It all sounds really good. Even if it's only available on one platform, we really should be exposing it. So I'll give you some concrete examples of how we might plan on adding this stuff in the future. This is not, I don't have pull requests for any of this as is. It's all going to require RFC. So it's still in the works, but it's just to give you a taste of how this might all fit in. So the first idea is kind of a socket API. right now I showed you we have TCP streams and UdpSockets and TCP listeners. But it turns out when you want to listen for incoming connections, that's actually a multi-stage process. You have to create a socket, you have to bind the socket, then you have to listen on the socket. And those 3 steps are configurable all along the way, and we're not actually exposing that. We just have this one constructor bind, which you saw earlier. So the idea is that we might have a lower level socket type, which is kind of abstract over the protocol, and I kind of give you each independent operation. You can configure it along the way, you can do your own binds, your own connects, set all the various options you want. One big thing for this is ESA reuse adder or reuse port are some fun stuff that people have requested on various platforms or various TCP listeners or UDP sockets. And then the idea is this can all be packaged up later and actually convert to one of those TCP streams or UDP sockets. So this is a totally separate structure which can be added at any point in the future backwards compatibly. And the idea is that level of advanced configuration, we're not adding that in we're not going to add 20 constructors to each of these types. We're going to kind of leave that advanced configuration for this type to kind of come into the standard library in the future. And one other very helpful thing, I'm sure Carl will talk about this with MIOs, we will provide a lot of conversion traits for going in and out of the standard library types from their raw representations. So for example, on Unix, we're going to provide a way from a file descriptor, you can actually get a TCP stream. And that is possible because we have lowered the representation of TCP stream itself to just a file descriptor. We no longer have this extra abstraction layer of arcs or extra file descriptors or anything like that. And I was talking a little bit about Windows permissions, where Windows has like this whole security attribute structure where it has all this fun stuff going on down there. And we can add all these as extension methods to the permissions tree. And then from there, we can on Windows give you a very nice API to configure all these in very rustic fashion, rustic style. But you clearly opt into the Windows-specific functionality when you're doing so. And with an opaque structure where we're able to kind of add the readers and writers of these attributes at later dates. All right, so that's kind of all that I have today for Stud.io FS and Net. Do we have any questions?
So does that mean that if I create my own type of, or can I bring my own file socket type, such as a timing socket or Bluetooth socket or something, and then just call from FD and then get all of the rest of your methods from it?
It's true. I think it's kind of we haven't quite fleshed out these traits just yet. They don't quite exist. So it's kind of uncertain whether they'll be unsafe or safe or anything like that. But the idea is that if you have a file descriptor, which is just an I32, we're going to pass it down to the system API, and it's going to tell us something. And it's kind of up to you as to whether that response is actually meaningful in some sense for you. So there are cases where it will go awry. But the key idea is that every operation you do, you know exactly what's happening. So if you call read, you know it's just going to call the read syscall. And you know if it goes wrong, you know precisely why it went wrong. It wasn't because we had some sort of select call in the middle, which did this really weird thing which you weren't expecting. So the idea is that you can get into these weird situations, but you know if it goes wrong, you know exactly why, because you essentially know how it's implemented.
Hey, so I had some questions about, let's say, the exotica of I/O. So how about things like Unix domain sockets, FIFOs, that kind of thing?
That's a good question. So that is one thing I left out of the StudNet module, which is we intentionally left out Unix sockets and name pipes from this iteration of StudNet. And the reason for that is that right now it's kind of loosely based on the libv APIs, which kind of gave you this abstraction which was the same across Unix sockets and name pipes, but they're actually very different APIs under the hood. So what we wanted to do is leave them out for now and bring them back later in their full-fledged glory. So we're going to have, on Unix, you'll have Unix sockets, and specifically Unix sockets, all that fun stuff. Whereas on Windows, you'll have name pipes and only name pipes, and you'll have all their fun stuff as well. So these don't currently exist, but we do plan to add them pretty soon afterwards. they will most likely reside in the std.os module. So you'll have std.os Unix, Unix Stream, or Unix Pipe, or something like that. But these are all details that will probably be fleshed out in future RFCs as well, because there are some interesting questions about the exact organization of the std.os modules and how these should come in and all that fun stuff. But yes, we do plan on adding them in the future. They just don't currently exist today because the implementation did not do them justice.
Okay. You hinted a little bit at like a std process or something like that. Can you maybe talk a little bit about what the thoughts are for that?
Sure. So std process is primarily the old std old IO process. It hasn't changed a whole lot. We still have this command type, which is a builder for new processes, and then at the very end you spawn it. But there are some tweaks in semantics of, such as when you spawn, do you inherit the file descriptors or do you capture the file descriptors by default? And then the actual process type itself is no longer called process, but rather called child. So we can later add a process type, which represents a remote process. And then it has some other differing semantics in terms of matching std thread, actually, of when you spawn it, do you actually join it, or do you wait for it when it drops, or do you actually let it stay detached and go off into the void? And we've scaled it back a little bit, so there are some configuration options which are now only available on Unix as opposed to on Windows. And we plan on continuing to expand that list of what fun things can you do on Unix versus what fun things you can do on Windows. But the general story is it's pretty much the same. We felt it was pretty good to start out with, and it was conservative. We can add new stuff to it in the future. And the major piece we lost was just timeouts, and that's because on Unix we had to spin up a helper thread, which is never really a fun thing to do.
So we heard that std.io is mainly blocking APIs for now. How much of std.net is also blocking or non-blocking? What works for both?
Currently, the focus is still on blocking, basically across the board. stdfs, std.net, std.io, all of it all around. But we do. It is basically designed so it is possible to add a non-blocking support in the future. The non-blocking support would currently look like set non-blocking, and then you just get tons of errors, and you got to figure out something to do with it yourself. We're probably not going to be binding epoll or KQ or select anytime soon, but if you somehow manage to even pull out the file descriptor itself and set it to non-blocking mode, and then you call the read API, you know exactly what's going to happen. You know that behind the hood, we're not going to select on it and then go wait for it indefinitely and actually call it in a non-blocking fashion. So the idea is that currently there's not great non-blocking support or async support or anything like that, but if we add it in the future, you know exactly what you're opting into. All right, thanks so much.
All right. Hi, everybody. I have Carl here from Portland, who will be speaking remotely about his asynchronous I/O stuff. Mike, I don't see the microphone jack. Wait. Yeah, don't start yet if you can hear me.
If you're using HDMI, you don't need.
Oh, yeah.
That's what
Okay.
you need.
HDMI. Let's get sound. Okay. Whoops.
Yeah.
Okay. Can you try it speaking? Am I on? You are not yet on. Okay. Sound. Still coming to my machine. Oh, this is, yeah, I forgot.
Yeah, within the application. Yeah.
Yes, okay. Where's that? Microphone, nope, that's, can you try speaking, Carl? No? Oh, HDMI. Okay, try speaking now.
Hello? Hello, I'm speaking. Can you hear me?
Are we muted? And setup.
Sound should be coming from my end. Oh no.
Please hold. Okay, can
Technology.
you speak?
I am speaking. Yeah, I see the little green dots. I see the little green dots on my end at least. I hear you.
See. Can you just keep speaking?
Hello. Yep, I'm speaking.
All right, we're
1,
good.
2. Oh, can everybody hear me now?
Okay.
All right. Well, my name is Carl Lurch. This is the first time that I am doing a remote presentation, so it's going to be a bit weird on my end. I can't see anybody, so I'm just kind of sitting in my basement right now talking, and I guess you guys hear me over there. So I'm up in Portland, Oregon. I work at Tilda, where we're actually a Rust shop. Well, we have a product that is a product for Ruby on Rails apps, but the agent runs Rust. So I think that we were the first production deployment of Rust, and right now we have, I guess, Rust code running in thousands of servers, and that's kind of exciting. And I think we first shipped the Rust agent back in March last year, and if you've been following Rust, you may know how many changes there have been since then. It was definitely a rough time to keep track. Anyway, so I guess we could switch the slides and go from there. I'm also trying some new slide software for this, so everything's brand new. Hopefully it'll work. Let me know when the slides are up.
All right, hold on. They are coming up now, and let me make you small. Okay, all right, you're good to go.
All right, so I guess this is my Twitter handle. I'm not going to be there in person afterwards, so if you have any questions, you can always hit me up on Twitter, and I'm on the Mozilla IRC server with the same handle. So these are just some of my Rust projects that I have on my GitHub right now. I'm going to be talking about MIO specifically, which is a non-blocking I/O library for Rust, written entirely in pure Rust. And I'm also going to touch a bit on Syncbox towards the end. I'm not going to talk much about Nix or bytes, but those are actually dependencies of MIO. Nix is kind of just started as where I dumped a whole bunch of system bindings that Rust didn't provide, and just kind of grew from there. And the goal is to try to have coverage for all of various POSIX APIs. And bytes started in MIO, and I extracted to its own repo as just a bunch of utilities for working with sequential bytes. So I think the main thing that I just added is a rope implementation, but I'm not going to touch too much on it today. So before I get started really talking about MIO, I want to kind of do a high-level quick discussion of asynchronous I/O in general. And what I mean by asynchronous I/O, I'm going to mostly talk about network APIs that never block the current thread that they're called on. So I know there are other file system asynchronous APIs and other various asynchronous APIs. I'm going to kind of just focus on the network ones. And before you get started that, I want to do a little bit of myth busting, because it seems to be like whenever there are various conversations and discussions about asynchronous I/O, a lot of kind of myths get thrown around. So I just want to quickly address them and kind of frame the discussion. First, some things that get said a lot is it's just fast because it's async. Now, it doesn't matter. It's just because you're using asynchronous I/O makes the code fast. Kind of the inverse, it's fast because it never blocks on I/O, implying that if you use synchronous I/O, your code is going to be slow. It's fast because it's close to the metal. Somehow, using asynchronous I/O gets you closer to the CPU, I guess. These are all kind of quotes I found, like preparing, just kind of Googling around the internet, finding blog posts and whatnot. And also, it's fast because threads are expensive. And kind of thinking about reading these discussions, it seems like if you spawn up a few threads, you're basically mining for Bitcoin. But this kind of impression I get, async I/O, and here we go, sync I/O. This is a lot of discussions around async I/O kind of paint this picture. So reality, well, first, yes, asynchronous I/O can scale to more connections when it's done right. And the big caveat is when it's done right, because in my opinion, once you go async versus sync, things are a lot harder. Like, it's really a lot harder to write correct code. And really, and I'm going to put this here, sync IO is actually faster. So if, like, when you have fewer connections, fewer network connections, and you're doing just working with the IO, if using blocking IO is going to be faster. Part of this, and I'm not even going to bother with micro benchmarks because at this point, honestly, you could shape them to tell you whatever you want. But if you think about it, when you're using sync IO, you are making fewer syscalls. You are deferring much more to the kernel, which will know more about what's going on and will be able to make more decisions. And so a lot of this comes down to scheduling. So again, like I just said, with synchronous IO, you are deferring the operating system to do scheduling. And by scheduling, what I am talking about is how are system resources assigned to tasks. So when you write code, you're really trying to get a job done, and the scheduling, it provides the system resources to do that job. And for example, when you have one task per thread, the implication is that you're writing the job to do synchronously, and each line of code depends on the previous one. So, aka there's the previous line needs to run for the next one to do its job. Obviously, the compilers are able to optimize this, but at a high level, the dependency of the task that's running on a thread is sequential. And given many tasks running on many threads, the operating system takes charge of the scheduling CPU time. When the blocking IO call is made, the operating system is able to schedule another thread in the meantime. So it just takes charge of ensuring that there's constantly code running, utilizing all the resources as possible. However, when there are many tasks per thread, you take the scheduling away from the operating system and take charge of it. So you're basically, you're just saying, hey, OS, give me control. I'm going to do a better job than you. And sometimes that's true. Like sometimes when you're handling very large numbers of connections, and you're able to juggle them more appropriately because you know what you're doing with them. But when it comes to fewer connections, that's not usually the case. So with that out of the way, I'm going to jump straight into MIO. And somebody just asked a question earlier to Alex. Would Rust standard library support non-blocking I/O? Personally, and I may be biased, but personally, I don't think the Rust standard library should. One reason is that there are many, many, many different ways to do non-blocking I/O. There's like the readiness model, which is basically saying, hey, here are a bunch of sockets, let me know when the socket is ready. There's the completion model, where you have a bunch of sockets and be like, hey, operating system, here are a bunch of sockets, I want to read from them, and the OS gives you back a chunk of bytes, so it will directly read from them. And there's strategies of passing callbacks, strategy of just blocking on a bunch of things and going from there. There's many different ways of doing it. There isn't really one right way. There are pros and cons for each one, so it's going to be a very opinionated stance. Whether something can be merged into standard library is kind of up in the air. So I'm just going to put that out there. I've had many discussions about this with Aaron and Alex. So MIO specifically provides very lightweight non-blocking I/O. And by very lightweight, what I mean is that it tries to be a zero-cost abstraction over the operating system's APIs. And specifically, right now at least, it focuses entirely on the POSIX API. So Linux, right now it's tested on Linux and Darwin. So Windows support doesn't exist now. It's going to be trickier for many reasons, so I'm going to kind of gloss over. There's no Windows support right now, but I kind of have some ideas to tackle that. Also, that was that slide. Also, on the lightweight, it's zero allocations at runtime. So once you boot up the event loop, and I'll be showing examples, once you boot up the event loop, MIO itself does not allocate ever. It does really as little as possible, and that design decision might forced kind of less ergonomic API than you might be expecting, but it's low enough overhead so that you are like other libraries, and I think Jonathan's going to be talking about this, can provide various higher level abstractions using MIO. And that's really kind of the goal of it right now, was just to be the bare minimum non-blocking interface. So it provides three main features. One, I/O events, and hopefully, because it's a non-blocking I/O library. You basically provide a bunch of sockets to MIO, and MIO will call back into you, telling you that the socket is ready to operate on. So this is, again, the readiness model. It provides timers. So it's going to provide an efficient timer API. You ask MIO to notify you after a set elapsed time, and MIO will do so. So I'll just call it right now. The timers are highly granular. What that means is you cannot have a finer grained timeout than 100 milliseconds by default, although it's tunable. The reason, and also it's fully implemented in the library versus deferring to system features like I think it's timer_empty. So I got the question before, why did I decide to do that? Well, one, MIO was focused on I/O, and in those cases, a very granular timeout's okay. Like usually, you're setting timeouts for seconds in the future. Sometimes hundreds of milliseconds, but very, very rarely do you set a timeout for just 10 milliseconds. And given that, it's possible to implement a timer system based off of hash timer wheel that is extremely efficient for very large numbers of timeouts. Like, it's possible, like assuming a min timeout of 100 milliseconds and let's say a max timeout of like 5 minutes, you could set up the MIO's timer system to have essentially O of 1 on timer creation, timer expiration, and timer cancellation. It really just ends up being a few like instructions, no matter how many timeouts you have in the system, as long as they're within a sane range. And the ranges are configurable. It also provides what, I don't have a great name for this, but cross-thread notifications. Basically, it has an API similar to Rust's channel feature where you send and receive messages, but the difference is that the receiving end is on the event loop and it's tied into the event loop, such that when you send a message to an MIO thread, it knows how to wake up out of like a poll. Like if it's waiting on messages, like if it's waiting on sockets and is blocked in the event loop, the notification will wake it up. It'll also be smart about when it iterates through the loop. There's some optimizations around whether or not to go back to sleep, whether the pending messages, and those kind of things. So jumping into it, just going to throw some quick code samples, and I guess in true Rust spirit, I actually broke some of these APIs since Aaron started talking, but just very minor. Like maybe I'll point it out, whatnot, but it's not that big of a deal. Anyway, so just getting started right now, and this specific API is also in Flex because part of cleaning this up was waiting on all of the IO reform stuff that you guys just heard about. I actually have been harassing Alex and Aaron a large amount over months, mostly like complaining about how I had to re-implement all the socket types, and I didn't like writing more code, and please allow me to just use Rust standard library socket types in MIO instead of re-implementing it. And I believe now it's possible. I've not done the work yet, but so hopefully, right now when you see TCP socket, that's actually an MIO TCP socket. Hopefully in a week or two, that will be the Rust standard library types. So here, basically what I'm doing is I'm just parsing a socket address. I'm getting the address. I'm initializing a socket, a TCP socket, and then I'm connecting to it. So the connects, so right now the MIO TCP socket, when you initialize it, it by default sets the socket to non-blocking. When I change this to use the standard net types, there will need to be an explicit step to say, oh, and I want to set non-blocking on it. because actually it's, while MIO is definitely geared around non-blocking sockets, it's definitely very possible to use them with blocking sockets. So you could have two sockets in blocking mode and just wait for something to, like, you could still use the event loop, wait for data to come in, and then pass those sockets, like, I know this socket's ready, pass it to a thread pool, and the socket's still in blocking mode, and work on it there, and then when it's done, return it back to the event loop, for example. Something that could be done. So in the future, you'll need to do create a standard net socket and then set it to non-blocking mode and then issue a connect. And the connect here is not going to block. The next step is, before you operate on it, you create an event loop. And that's, I didn't put all the imports, but I can post the gist or the code snippet, entire code snippet with the imports and whatnot later. You create the event loop, and you register the socket with the event loop. So this is part of the maybe slightly less ergonomic API, that's something that you may not expect, but it was done in order to provide a zero-cost abstraction over epoll. So the first argument here is just the socket. The second is the token. So what's going to happen is, when you register a socket with the event loop doesn't take the socket, and it's not going to return the socket later. It's going to take the token and then notify you with the token. It's going to be, and the token is just a wrapper around, I think, usize, because I take the token directly and pass it to epoll, and epoll only takes a pointer-sized type. So it'll be your job to figure out how you're going to store the socket and get it back later. One way, like, I think these code samples that I have are a bit simple, but one way, MI also comes with a slab abstraction where you can pre-allocate storage for large amounts of sockets, for example, and just store them in there. So okay, so the token second argument went over. Next is the interest that you, like the socket interest that you want. So here I'm just going to say all, but you can say I only want to get notified on when the socket is readable. If the socket becomes writable, I don't care, don't notify me. Or you could do the reverse, or you could say only tell me when there's an error. And the final argument are the poll options, and here I'm saying edge and one-shot. But basically edge with epoll and also KQ and the various non-blocking I/O kind of polling systems, there are two different strategies. There's edge and level. Edge notification means that, now I'm like on the spot and I'm tired, I'm going to get it reversed. Edge means that once you get an event from the epoll, you get the socket back saying, okay, here's this socket's readable. Unless you read from the socket, epoll will never tell you again that socket's readable. So let's say you get the socket back saying, oh, it's readable, and then you do nothing with it, and you do another loop of the event loop, you're not going to get notified of that socket again. The opposite is level. And in that case, on level notifications, if you don't do anything with the socket and you loop again, you'll get the socket back with another notification saying it's readable. So the general things like, so edge, supposedly level notifications are easier to use, but they incur a higher cost in the operating system because the OS has to manage far more data, I guess. And then here I'm also saying, I want edge notification, which means every time there's a change in the socket, notify me, but never again for that same read. So I get the socket back, it's readable. I read from it, I loop again, the socket becomes readable a second time, I will get the notification again. But with one-shot, when I specify one-shot, I'll only get one single notification for that socket. So if I then get the socket and I read it, and then I want to get another notification for it, I have to register it again with event loop. So that's kind of the brain dump of everything here. Hopefully, most of the information of like how this all works is, since it's the very thin wrapper around epoll and KQ, you can read the epoll man pages. Hopefully, MIO itself will have more docs. Since this is mostly just me working on it in the spare time, docs are a little lacking. There's some, but it could use more help. So hopefully part of why I'm talking about all this is also I would love help on these projects. Anyway, moving on, the next step would be to start the event loop. So up until now, until you start the event loop, there's going to be you're not going to get events. So to get events, notifications, you create a handler, and the next slide is going to show you the handler trait. And here I'm just simply doing, okay, I'm going to make, I'm just storing the TCP socket directly, and I'm going to use a slice buff. So this is my buffer abstraction, which a large part was inspired by like a combination of Java's byte buffers and Netty's channel buffers, which I think were renamed to byte buffs. I don't know if you're familiar with them, but it's the combination of sequential bytes abstraction plus a cursor, so that whenever you read and write, it tends to be like, it'll update the internal cursor. I think I was only casually listening. Alex may have mentioned that something similar may have landed in Rust standard library, but I've not looked at it yet, so I'm going to have to do that later. So you make the handler, and and here's the full trait for the to define a handler. One, the readable. The event loop will call you when a socket is readable. It passes in a reference to the event loop so that further changes can be made. Again, it just passes the token, so then you can use that token to look up the sockets in whatever storage you use. And it also provides a read hint, and that read hint that again also comes from EPL. Basically, read events, error events, and like EOF events all are notified to readable. So the read hint kind of gives you, it lets you know what kind of events you'll get without actually reading from the socket. And the reason why it's a hint and not the actual event is because not all platforms support it. So if you look at the read hint and see EOF, you know it'll be an EOF. But if you don't see anything, there might still be an EOF. Writable, you get notified with that a socket is writable. Notify is when you receive a notification from another thread, and timeout is how the event loop calls you back when a timeout expires. So here's so we set up these sockets. We called connect on it previously, and we register with the event loop. Now MIO will notify you through the writable event when the socket has fully connected. So when it's fully connected, it becomes writable. And here, what we're going to do is, I think we had the slice buff on the handler, which is the message that we're going to send over the socket. Part of the thing with non-blocking I/O is that, okay, so while there's remaining data, we're just going to call and try to do a write on it. And this is an MIO trait. I'm going to try to have to see if I can reconcile the MIO reader and writer traits with the new standard Rust standard stuff, but the MIO write trait will return a result, and it will also provide an enum. The successful result is a woodblock or a ready. So basically, what we want to do is, if we hit a woodblock, which means the socket is no longer ready, we want to return from here because there's nothing else we can do, and then MIO is going to call us back. Well, basically, this writable function may be called many times before the buffer is fully written to the socket, which is part of the complexity of dealing with non-blocking I/O. So this entire function has to be able to just resume from the point it was at every time it gets called. And finally, at the very end, for now, what I'm just doing is shutting down the event loop. Once the message is fully written, the socket will get closed, and the event loop will shut down, and all associated resources will be cleaned up. I'm going to add how you do timeouts. So now, instead of just writing a socket and closing it, the general idea is we're writing a message, and then we're going to wait for the response. The above code is the same, but what we're going to do is set a read timeout. And this is also in flux because I just used the duration type in standard, but that supposedly will change sometime soon. So here we're tracking the read timeout allows us to cancel it in the future. And then we call event loop timeout with, here I'm just passing the socket token, so I get, when the timeout gets called, when the timeout callback's called, I'll get the socket token, and I'll know which socket which socket timed out. So now let's look at the readable side. The first thing we want to do after, when we get the readable messages, we know the socket's readable, so we want to cancel the timeout. Because we don't want the read timeout to trigger later down the road since we already know the socket is readable. So I just take out the read timeout and I call event loop clear timeouts, and now we're going to read from the socket. Here I make a byte buff, which is very close to the Java byte buffer style. I start with a mut byte buff 1000 about a k, and I read from the socket. While the socket is still ready, I just flip it and I do something with the bytes I just read, and I flip back so I can resume. So I'm not going to dive too much into the details of the buffer, but the general strategy here is as long as the socket is ready, I need to keep reading from it. And I didn't implement the code snippet, but you probably once you get woodblock, you probably want to do something to track that you have the state in which you're at so you can resume. And this is what the timeout function might be. So here, when I get this, I know the timeout got triggered. I'm asserting, just because I've only worked with one socket here, one token here, I'm just asserting that the tokens would expect, and I'm just going to shut down the event loop here. So that's like the really quick MIO intro. I think the best way, if you want to get more familiar with the details, in the repo there's some documentation, and there's a whole bunch of full integration tests where there's like an echo server implemented, and there's like UDP. I think right now we support like TCP, UDP, Unix domain sockets. I think, what else do we? There's probably something else. Anyway, the main kind of selling point of MIO is that it's fast, and by fast, like I said before, it's a very low level, like zero cost abstraction on top of the system. And again, that is kind of what I'm trying to focus on. And like I showed before, I focused mostly on the readiness strategy. And the readiness, like I mentioned again before, the readiness is that when a socket is operable on, the MIO doesn't read directly from the socket and give you the bytes. It provides the socket so that you can decide whether or not to read. And one very legit strategy is you know the socket's ready, but you're not going to read from it directly. And this strategy allows you to avoid what is, like if you're writing a proxy, kind of a double buffering, where you read from the clients into one buffer, and then you have to like write to a different buffer before writing to the server end. And the way you might implement that in MIO, like you can implement a full proxy that only has a single allocated buffer. And you do that by juggling whether or not to read from a socket even though it's ready. So here I'm just going to set up a very quick proxy. I'm setting up the client socket. I'm setting up the server socket. I'm going to have a Boolean flag that lets me know if the client socket is ready. I'm going to have a Boolean flag let me know if the server socket is ready. And I'm going to have my single global buffer. So here, next again, I set up the reading and writing from the. Sorry, I'm kind of tired. The sockets with MIO, and what's important here is registering it as an edge notification as well as one shot. Because once we get the notification, we don't actually want to get another notification because we may not read from the socket directly. And this is what the readable and writable ends might be. So in readable, we assume the token is the server one, and I feel like I messed this one. I did this one backwards. I didn't actually execute this code. Anyway, the general strategy is when token is readable, we then flip the state of it, and then we attempt to proxy the data. Again, on the other end, all we're doing is tracking that the socket is ready, and then we call try proxy. So even though we call try proxy, it's not going to actually do any work until both sockets are ready. Now, when we know that both sockets are ready, we can read from one socket directly into the buffer, and then directly from that buffer write it down back to the other socket without having to store that data past this one bit of code. So that this way, every single time multiple socket pairs are ready, we don't need to have any transient in-flight buffers. There are obviously complications. I'm not going to go into them in this quick talk. So now I'm going to get back to scheduling a bit. So when there's work to be done, there's many ways to schedule it, and I'm going to be talking about in the MIO case. We get a socket that's ready. What do we do with it? Like, do we read the socket directly as it's ready? Do we read it until completion? Do we read it a little bit and then reschedule the sockets for later? Do we put the sockets in the queue and then process them in a thread pool? Like, there are many really, like, a lot of strategies to use. And then one huge question that you have to think about when using asynchronous I/O is how are you going to handle back pressure? With sync I/O, back pressure is automatically handled for you. If a stage can't keep up with the work that's being done on it, it's just going to block, and then any stage that depends on that is going to end up blocking as well. That's going to proxy up. Once once it gets unblocked, everything else is going to cascade back. You don't get that out of the box with non-blocking I/O. You have to take care of figuring out how you're going to do that. If you don't handle back pressure, you're going to fill up the resources of the server, and the server is going to crash without memory errors. This is in part why if you're going to use MIO directly, it's much harder than just using sync I/O. However, ideally we wouldn't really have to think about scheduling. You would just define the dependencies of what you're trying to do. You would just work on the logic, the business logic of the code, and the details of whether or not a stage is scheduled or not would be handled for you. And this is kind of where I'm going to segue into Syncbox, which is much more in the in-progress stage than MIO. MIO can right now be used fully, like everything I showed will work. Syncbox is right now focusing mostly on futures and streams. And most of the core of this is implemented. I have some helpers. There's still a work in progress, and specifically binding TCP and I/O to a more future and stream API has not all been done yet. I'm going to show some examples of what it might look like, but that has not been done, although I am working on it in my spare time. I think I may be going late, so I'm going to try to rush through. Let's see. So this is what so let me briefly talking about future. A future is kind of like, the short version is, it's kind of like an asynchronous result. So just like the result that Rust have, a future is kind of like an asynchronous version of that. You call a function like HTTP GET, you're going to get back immediately without blocking, you're going to get back a future that represents the work that's being done, even though the work may not have been completed yet. But what that allows you to do is operate on the future directly before the work's done without worrying about the specific value. And you don't need to worry about the specific value until you ask for it. So let's see. Going into this code, there's a few things. So first, like I said, make the HTTP request, get back a future, and on the future we're calling map. We'll get the response, and we're going to map that to contact length. This map callback is not going to happen until the response is completed. So then we can define these two futures, and then further down we're doing a join, and what that does, so join is implemented, that primitive is implemented. What this says is, here are two futures, I want to wait until they're both ready, and then I want to operate on them together. And here I'm just going to dump the result value. What we've done here is essentially define a data dependency between the different stages of the code. We say we need to make two HTTP requests, but we have defined that these HTTP requests are not related. Once we do the join, at this point we're saying all the work previously we have a dependency on it. So we need to wait here for the work to complete. This can then, some of this is implemented, this can then be passed on to a separate scheduler. Right now, I think it runs on a thread pool, and it's able to handle the bits that can happen concurrently. It can handle them in different threads. Next slide. And then it'll handle the when two dependencies are joined, it'll handle waiting for both ends to complete and then execute the bits that come after that. So let's look quickly at a more complex example. If the TCP bindings were implemented, this is what a full TCP proxy might look like. And it fits, I think, in 10 lines of code. It's kind of nice. So first, the bindings, then we listen on the server. Listen instead of like blocking or instead of saying I would block, it returns what is a stream, and a stream is like the async iterator, so it's a sequential future values almost of sockets. So what it's saying, the listen returns a construct that says I'm going to keep providing you sockets as you ask for them, and then we operate on them saying keep giving me sockets until I receive a SIGINT. And this is actually kind of interesting. Like this function could be implemented as a future of receiving the SIGINT, which is Control C. So when you pass that as the condition to take until, it will just keep giving you the sockets from the stream until the signal is received, and then truncates the stream, and that will allow everything to shut down cleanly. Next, we iterate over each socket. We get the clients. It's kind of like a pair, like a client TX client RX, a pair just like the Rust channels. With this, we then connect immediately to the server sockets. Once the connect succeeds, we get the server end, and then we just hook the two together. And at the end, the async join, we're just saying here, let's wait until the writes are fully done and the reads are fully done, and define that dependency there. And then here, the await was just going to trigger the entire thing. And now would be a fully functional TCP server if SyncBox streams and futures were fully bound, and it would be able to run fully in parallel. And one important way that it works, and I just want to emphasize this point, the future is going to be lazy. So you can do something like this, where you see this on the second line, HTTP GET, we're issuing the HTTP call, it returns a future. The way this works is the HTTP GET call won't start until the future is observed, kind of. So in this case, if the first HTTP call succeeds successfully, the second one will actually never happen. And I know I'm kind of rushing through this, but one last point I kind of want to make, futures and streams are very functional constructs, and a future can only be realized with a single value. That value will never change, so it's kind of immutable in that respect. And while it's a very nice abstraction, and implementations tend to be costly due to the large amount of extra objects being created. And I say this because I tried to implement this previously, once in Clojure and once in Java, and it ended up having a large garbage collection cost due to the extra objects that were created in each iteration of the stream. And to really be able to use this abstraction, you want to be able to create futures and streams as cheaply as possible so that you can use them well everywhere. With Rust, I was able to use the very strong ownership concepts so that I know when a future goes out of scope, I can reuse the core. So like futures and streams are really just handles into an internal core structure, and I'm able to reuse that data often, so I reduce the applications. So that's what I have now. I think I forgot to time, so I feel like I got over, but again, Twitter, you can ping me with questions. GitHub, IRC on the same thing. Let's see, that's what I got so far. I don't know if I can get questions, but...
Hey, thank you. Does anyone have any questions? Okay, well, thank you, Carl. That was great. That was really neat. Right. Oh, and goodbye. Just like that, he's gone. Okay. All right, and Reem, I believe this should be your most recent slide deck. So, do you want to? Sure.
Get the urge to bring some.
Yeah.
Code or something.
Here.
All right, cool.
Yeah.
Thank you. All right. Hello, everyone. I'm that guy, Jonathan Reem. I have written a bunch of the web stuff in Rust. So things like Iron and Hyper are partly my stuff and whatever. That's basically the major intro. I've been doing a lot of work with asynchronous things in Rust, especially surrounding like Mio and doing asynchronous I/O and trying to get things bootstrapped to the point where you can do like what Carl was talking about, kind of like higher level I/O abstractions and whatever. So this talk is basically going to be, it was originally going to be a little bit more about kind of the libraries that I've been building out around this, but for various reasons, those aren't like fully done yet. So instead, I'm mostly going to talk about my experiences writing asynchronous Rust, what works, what doesn't work, and kind of how the patterns that arise differ from those that you get with synchronous Rust. So the name of this talk is plus static because when you write asynchronous Rust, you basically end up appending this bound to anything that can be, to every like trait object, and anything that could be a reference, like quietly, can't be. And this is interesting. This is because the event loop needs ownership, right? So you're talking about these asynchronous actions that can be scheduled. So you say, like, I have some FN once that's going to run at some point in the future, maybe 500 milliseconds from now, or like I'm going to do some timeout. You can't have any borrowed data in this action because that action could happen at any time. It could run now when the stack frame is still there. It could run on a different thread. It could run, well, not on a different thread, but it can run much later after everything is gone and all of your references you have are dangling. That's bad. So everything is static. This is pretty problematic because the borrow system is based on kind of like the static lifetimes of objects. And that's confusing because not the lifetime static, but just the fact that the structure of your code describes how long your objects last, or at least how long kind of like non-dynamic objects last. And this is weird because when everything needs to be static, this stops being able to help you. When all of your lifetimes are dynamic, right? Like whatever action that I know, it's not going to run in this block of code. It could run at any time. So this makes the borrow checking a little bit tricky because you sort of can't use a lot of the same patterns that you've gotten used to in synchronous Rust because things just don't work, like lifetime-wise. This sounds like a bad thing, but it's actually a good thing in a lot of cases. So Rust continues to enforce correctness here because when you compare that to, for instance, like in Node.js, right, or in JavaScript generally, you can set a set timeout to say that, all right, 500 milliseconds from now, set this variable to some value that you're going to get from elsewhere. It doesn't matter. You're initializing some data, you're modifying some data, whatever it is. You can continue in those languages because they don't have this concept of like ownership of you moving this object into here so you can no longer interact with it. They let you continue to reference this. So you can, in Rust, this isn't true. You can move when you move into an async action. When I say I'm going to use this variable in a timeout, I have to move that into a timeout. So I can't say, all right, initialize this whole structure, like do this request parsing later and initialize this request object 500 milliseconds from now, and then immediately use that request object after I've scheduled the timeout. I have to actually wait for some other mechanism to transfer the ownership back to me explicitly. And then you do the same deal with everything is static. So if you try and borrow into an async action, which isn't a problem in like managed languages, but it is a problem in like C or C++, if you try and move or borrow some, like reference some piece of data in code that doesn't run immediately, it's pretty easy to like get all kinds of dangling pointers and whatever. The borrow checking in Rust prevents this from happening. So this is a huge class of semantic errors that you see a lot with asynchronous programming, and especially I think this first thing about moving into an asynchronous action actually preventing use is super important because when you see at least I have a reasonable amount of experience teaching like new programmers or relatively new programmers Node, and you see a lot of the mistakes that people make when they're trying to think about like callbacks and just control flow that isn't what they see on the screen. They make all these mistakes, and I think that Rust using this system catches a lot of the like dummy errors, like using variables that might not be initialized, using data that just isn't yours right now. In the same vein, the whole fn once, fn mute, and fn split is sort of the thing that comes up a lot as this like very complex feature of Rust that is complex and it has all these variants because Rust's ownership system is complex, and so you have to have different modes of the closures for the different actions. When you're talking about asynchronous code, this is actually super nice because you get this kind of additional documentation, right? You have fn mute for one-time actions, like a callback, resolving a future. These are the kinds of things you use fn once for. So this lets the types like clarify the documentation of your functions. It lets you say, all right, this action is only going to happen once, so I'm going to use an fn once to represent what happens when it does. And this also lets the clients of your API like bank on these guarantees, right? So you can't go around changing your code and calling these callbacks multiple times if you promised you're only going to call them once before, or at least you can't without notifying clients by breaking your API. So this prevents another large class of common errors and things. People think callbacks are only going to be run once, and then they get called multiple times. You have this whole mess with some implementations of promises that they'll call your resolutions on progress, all kinds of ridiculous things like that, that the fn once, fn mute split actually clarifies, which is kind of nice. So you may be wondering why I'm talking about static, not send. Kind of a segue for a moment. Because we're talking about data that can be run at any time. You know, you might want to have the loop running on its own thread, and you have your thread pool where you manage all of your work, and so your event loop generates all these events that you need to do something about, and then sends it over to a thread loop and has the thread loop do that action. That would require that everything that you're sending forward has the send bound. It actually can be sent between threads. This is not like a huge deal. So loops are thread local, and that's partially to make the implementation simple, as opposed to this whole like thread pool and an event loop communicating with the thread pool. But really, the more important parts are about what the cost of having this like parallel eventing basically kind of going on. It's like it's difficult to think about both multi-threaded code and evented code and asynchronous code, and you're trying to combine the two, like you're asking for a headache. And this is really because of kind of the shared mutability that you need to do in a lot of asynchronous code, which is something that I'm also going to talk about. And if you want all of your asynchronous primitives to be able to be sent across threads and like shared between threads, you need to do things like use atomic reference counting for shares, but more importantly, for all of your interior mutability, everything needs to be synchronized, unless you're using atomics. But for the most part, most of your mutability needs to be synchronized, which is like a pretty large cost when you think about for instance, if you want to pipe a read stream into a write stream, right? You have some data that like gives you, that's like a non-blocking stream. It gives you a chunk of data every once in a while. And you want to pipe that into a write stream. And that write stream is like every once in a while it's going to say like, okay, I can have some data. They might, and this is where you get back pressure, right? So they might not add up. The read stream might yield a huge amount of data, and the write stream is like, I can read 100 bytes, I guess, if you want. So as a result of this, you need to have a back pressure buffer, someplace where you store all this data that the read stream is like dumping out at you, or you don't read it. That's the alternative. But if you are going to read it, you need to have a place to keep it, and this back pressure buffer needs to be accessible by both the reading stream and the writing stream. So if you want to have this, and it needs to be mutable in both, because the read stream needs to be able to read into it, and the write stream needs to be able to like advance pointers and whatever into that structure, so that it knows where to keep writing from or keep reading from or whatever. As a result of this, you end up using shared mutability a lot. If you're doing these things in a multi-threaded environment, you have to use locking, or other forms of this. So it means that your RC ref cell, which has a runtime cost, but it's very low, is now a mutex, or an arc mutex, which is a much higher runtime cost. And that runtime cost is paid on every single read and write event of both of those streams in your pipe, which is bad. When you do this kind of asynchronous code, like we were discussing, there are cases where you need to do sharing. And sharing it's tricky in normal Rust because of the ownership and immutability rules, but it's even more tricky in asynchronous Rust because you do things that aren't as well handled. For instance, when you move into closures, right, you use the move keyword in front of a closure, you move the captures of the closure into that closure so that you can, so that closure doesn't contain references to its enclosing stack frame, and you can send it off, you can return it or send it off to an event loop or whatever. The problem with this is that, like, if you look at, for instance, an if-else statement, right, you have some variable, so you have some vec, and you do an if-else, and you move it into both branches of the vec. You move it in both branches of the if-else. So if it's longer than 4, you drop it, and if it's greater than 4, you send it off to this other place where it does some other action. Either way, you are moving that vec into both places. If you replace that if else with a function that takes two closures, you can't do that anymore. When you move into, you can't move into both closures. So you can't be like, if this thing is true, move into this closure, else move into this closure. You have to move into the closure basically when it's created. It has to be part of like the type of the closure. As soon as you instantiate that closure, that's when the move happens. This means that if you have like asynchronous code that's like do this action and then do this action, or do this action or do this action, it's basically impossible to encode like the invariance of that. But like these closures can share some own data. They can both move out of this data because only one of them is going to run, for instance. You can't say, there's no way to say basically to the type system that it's okay for these guys to both own the same data, like you can with an if-else. It's basically both branches of the if-else own the same data, and you can like move into both of them. Not really, but you can, the compiler will allow you to write code that acts as if it moves into both of them, even though only one of those branches runs. This is like kind of a gripe that basically means that if you want to share an async tasks, or if you want to do things like only one closure, both closures, or whatever, basically everything requires that you reference count your objects, or you at least, if you have multiple handles to them, you reference count them, else you have to heap allocate them, which is kind of unfortunate. But basically, when you're sharing async tasks, and you have to use, when you use mutability, you have to use cell types, so ref cell and save cell, cell depending on your data and what you want to do with it exactly. And this is basically the largest pain with doing asynchronous code in Rust, is that there really aren't the sharing primitives that we need there to be yet, in terms of primitives for precisely sharing data between like closures that can run later. So there are a lot of hacks that you can use to get around these problems. Like you can, for instance, write a function which your if-else function, it's not just going to take the two closures and a condition. It's going to take the two closures, a condition, and explicitly all of the shared variables that those closures both need to move out of. And then the if-else function decides, okay, I know that I can pass this owned code into only one of these two functions. And so the closures that you pass into this if-else instead take the things that they need to move out of or that they need to share and move out of as arguments rather than them being captures in the closure. The problem is that these sharing patterns, like that's like a simple sharing pattern, right? You have two closures, one of them is going to run, you want to move this data into only one of them. That's an extremely simple pattern, and that can be codified. But if you look at like more complicated sharing patterns, can everyone actually read that? So this is a tiny example, or just like the header of an example between, this is from some pipe code, so from code that does that piping action that I was describing, where you take a read stream and you write each bit as it comes into a write stream, which also reads for those bits. So here, what we're doing is we are using this function to control the registration of both the read action on this stream and the write action on the write stream, so that they can both access this shared parameter s mutably. So you can see here that, like, I guess I can't step away because the mic. So you can see here, if you look at rs, or R and W, they're both fn1s, and they both take and mute s as their first parameter. So they both get this like mutable access to the shared parameter. And you get all these like corner cases, like the fact that after is here, it's this like other seemingly unrelated thing, where you now need to be able to tell also, because you're no longer in charge of figuring out when these closures run and how you're calling them or whatever. This function also needs to expose when did both of them run, or when is the whole thing finished. So you have to have this like after function. That after function then is the one who can actually move out of the shared resource. So this is like if you want to report that the whole operation is finished, this is basically a join. Like the after action, you can sort of think about it as a join and then a map if these were all futures, which is the ideal API is that everything is streams and futures and whatever, but internally you still have to have kind of this like mess of closures and callbacks, which is unfortunate. This is when you're sharing between two closures. So the problem is that you can't just reuse. It's difficult to reuse sharing code because you don't always control the registration of the closures. In fact, in most cases, when you're writing library code at least, you're not the one who's actually in charge of scheduling actions to run. You're just writing code that, like, if everyone acts appropriately, will schedule itself. But it doesn't schedule itself. So, like, in this case, you can't just pass the closures because the streams, so RS and WS and the read and write parameters, which are your streams, are actually the ones in charge of registering. So you have to pass those along too. You basically this is the result of kind of like trying to get these like ad hoc combinations to work in a general way. So you don't have to keep writing the same unsafe code. Like the internals of this are unsafe for surprising reasons, but mostly to do with the way that you have to share whatever. This function is about 40 lines total, with about 20 lines of types in here, and some help and additional helper functions that you had to write. Which is another note is that the types of these things can get really gnarly in the sense that nested closures and dissociator types and closures that take other closures and all of that can get very verbose, and I don't know, it can get very verbose. And this is like kind of a sad case. What does work? So what does work really well turns out to be functional programming, or not necessarily completely pure functional programming, but like functional-esque programming. Basically, you're talking about functional pipelines over mutation. So dealing with, as we've seen, like dealing with this kind of like shared mutability and all these kind of primitives is a huge pain when it comes to asynchronous programming. And you also can't really, like, you're constantly fighting in terms of like the bar system, that you can't have these like references and like mutable handles to objects and stuff like that. Everything needs to be owned. Everything needs to own its own data, and that works really well with functional programming, where you have all these values, and you don't have like mutable references or whatever. You just have discrete values that all own each other, and you're just passing them around. And that works super well. And then you also have this like nice property that a lot of like asynchronous concurrency primitives like futures and streams are both monads. And like if you have future as a monad and you have do notation, you basically have async await, which is kind of cool. And you can do all these other interesting things. You have all of these higher order functions that really encourages a lot of functional programming patterns and determining basically just the control flow and how you knit your code together, sort of. You end up writing a bunch of combinators over functions rather than like combinators over like values, which is kind of interesting. And my prediction for this is that the best way to kind of work with asynchronous code in the future with Rust, both in like asynchronous I/O and like web programming, and then like future endeavors into just like using eventing for other types of code, like just general UIs and all that kind of stuff. And I think that functional reactive programming and the ways that it's manifested itself in other languages, you can see like Java, like RX, and all of those I think that's really the way forward with Rust. So we're talking about streams and futures as like the main building blocks, like Carl was talking about with Syncbox, and other APIs are basically going to be built mostly on top of those. So in terms of examples, this is like a very simplified kind of a stream trait from things that I've been playing around with. The things that this trait is missing include errors, or at least, well, you know, I didn't run this code, but it mostly, this doesn't include errors, but it includes basically everything else. And so the interesting thing to see here is that the only reference in this entire thing here is this one little lone and mute U8 here, and that is basically only an implementation detail of trying to avoid double buffering. And if you think about mutability as an implementation detail, and you sort of think about your APIs as more like I do this thing and I get these values, or I get these promises of values, or whatever it is, it doesn't really matter. The whole idea is that your APIs will compose a lot very nicely with asynchronous code if you deal mostly in values rather than in references and mutability. Something to think about. Gripes. So I have a few gripes for my work with asynchronous code. One of the big ones, which doesn't come up in a lot of Rust, but it comes up a lot when you're writing kind of these like function pipelines where you end up with like recursive closures and whatever, is that you can't write a recursive closure using the pretty notation at the bottom. There's no action that allows you to reference like self in the closure, basically, and this is more of a quirk of the syntax, really, than I think anything limited by the actual implementation or technically, because it's pretty trivial to lift out the closure into a struct with explicitly capturing all of your captures and implementing the traits on it manually and then referencing self in those trait impls. Or lifting it out into a function and having all the arguments, all the captures just instead be arguments. The lack of type inference on function and method signatures, and that makes doing this pretty unfortunate. And this is actually like, this looks like a complicated type signature, but it's actually a pretty simple type signature compared to a lot of the stuff that you end up with when you have a bunch of like generic captures and all of this other garbage. So when you try and lift out these recursive closures into recursive functions or explicit structs, that like is a lot of code load. Like most of the 20 lines of types and all of the majority of the implementation for that shared function is basically just dealing with no recursive closures. Yes, we all want higher kind of types, we all want monads, it's cool, whatever. And that there is no inference for method types and impls. I understand the motivation for not having inferred types for functions in general, because it like distances the site of an error from the actual site and all kinds of other pretty good reasons. But when you're dealing with trait methods, like the type is already set for you, there's nothing you can do about it except get it wrong. But the fact that there's no inference means that when you're writing traits that other people are supposed to implement, you have to work really hard to keep the type signatures reasonably clear and have like very limited imports as possible and all kinds of other things. And that hurts when your traits start getting really complicated. A little bit about future plans. So we talked, Carl mostly covered Mio and TikTok, so I'm not going to talk too much about that. And the rest of this is projects that I've either been working on or plan to work on in the near future to kind of paper over the whole kind of tattered asynchronous I/O situation and make things more like usable and kind of ready. So starting from the top, we have Rust event is just a very, basically a very thin wrapper around Mio that takes care of a lot of the boilerplate associated with Mio. So a lot of what you saw in the examples from that Carl was talking about was there's a lot of stuff with just like setting up the event loop, just like calling the right functions, creating your tokens, creating your handlers that control the tokens, and then matching the tokens when you get back. All of this stuff that is basically the same in 99% of applications, and the 1% that needs more flexibility just can use Mio directly. And Rust event papers over all of that by kind of taking care of it for you. So you get the same almost the same implementation, with the addition of like you end up with one virtual call per handler, which is unfortunate, but mostly unavoidable, or actually entirely unavoidable, if you want to have like a nice kind of callback-based API. So Rust event is like just that super thin wrapper. It doesn't produce any of its own types. It doesn't like do a lot of addition. It doesn't do basically any additional work. It's just like a very simple wrapper around Mio, takes care of registration and calling of your handlers. It also has nice APIs for like the equivalent of like process.nextTick from Node and set timeout and set interval. That's it. Rust chunks is something that I haven't published yet, but I've been working a lot with. That's basically just like stream traits and a bunch of utilities for working with streams. So things like pipe, T, a whole bunch of other utility functions or whatever for dealing with all kinds of data that comes in chunks, basically, as opposed to all at once. And then there's Rust AIO, which is sort of the big one. Rust AIO is the goal is for it to be a final implementation of asynchronous I/O that rolls in a bunch of stuff from Mio. It uses Rust event, uses the types from Syncbox, so futures and streams, and it rolls us all into a very nice, like really easily digestible package. Something that like mirrors what standard I/O looks like, but for asynchronous code. So that's going to include, and there are a lot of like really interesting things that you can do here. For instance, Now that Mio will be able to use the same types as standard I/O, Rust I/O actually kind of shrinks a lot because it can use the same types from Mio and the same standard types, and end up most of the implementations are just trait implementations, extensions, and adapter types, which is like a much smaller scale than like rewriting all of the basic bindings for all of the basic I/O types. So I heard about that, and I thought that's a really good step forward. Then you have Rust sharing, which is basically going to be a bunch of utility functions for dealing with sharing mutable data in asynchronous code and between closures and all of these kind of tackling a lot of the problems that I talked about, and trying at least to codify a lot of these like common patterns so that you don't have to write this code yourself, because it's a pain. And then all the way at the bottom we have like Rust async, which is eventually, and that's mainly just a collection of traits surrounding asynchronous programming, so that right now there's a bunch of variations on all these traits. So like eventually when we get higher kind of types, we'll have a future trait and a stream trait and all this stuff. Future requires higher kind of like a future as a trait requires higher kinded types for now, which is unfortunate. But Rust async is going to be the library that basically just contains those traits that instead of being scattered all over different libraries so that they like aren't compatible, everything just goes in this one crate, and that crate and all the different libraries will use this crate, and so they're all kind of using this common set of basics, which is good. Good job. That's it. Super quick plug. I have just entered the job search, so if you have any interesting things to tell me, send me an email. That's all, folks. Questions? Yeah.
Have you heard of anybody playing with disruptor-style patterns in Rust? Do you know anything about that?
Unfortunately, I do not. Short question. Anyone else? I would be happy to talk to you more about it later.
So yeah, as I was listening to the beginning of your talk, just all the troubles you had with immutable state and like how do you manage it and that kind of thing. Like my initial reaction was like, you really need FRP. So the fact you're like, yeah, we need FRP is great. But for the mutable state, yeah, I was thinking the exact same thing, that you need something more like disruptor. So I'm a big Martin Thompson fan, but just the idea that you have these sort of like lock-free, wait-free data structures, you can take sort of like a slot in them as a slice and send that around to like a thread pool. So you have effectively like an event source and a thread pool that's consuming that.
So the disruptor is like the source of events.
Yeah, but the idea is you have something like a ring buffer.
Okay.
Right, so you have a way of putting data into one of these slots in the ring buffer and sending them off to a thread pool to be consumed. And that way you're not juggling all this immutable state and you don't have to pull in like reference counting and that kind of thing.
Interesting. Yeah, well, I don't know. That sounds cool. I'd be happy to talk more about it.
So just to try to answer your guys' question, actually there was a disruptor implementation in Rust that showed up a few months ago. I haven't heard anything recently about it, but you could probably dig it up.
Yeah.
It looked pretty solid.
I was just going to say that I think there are two actual disruptor patterns. There's Rust disruptor and turbine, which I think are both variations, but at least according to GitHub, they haven't been touched for the past couple months. So they're horribly broken now.
Yeah. Okay, well. Anyone else? Questions? Thoughts? Comments? All right. Thanks, guys.
Yes.
All right. Thank you very much. This is a close. We, I think, have the room for a little bit more, so please feel free to hang out and have pizza and have a good night. Thank you all for coming, and see you in a month. Goodbye.